Okay, so yeah, let us begin. What happened to you? Okay, so we want to understand in this lecture like how chaos can be used, like use of chaos, the use of chaos in in sending secret messages. Okay. So make sure like I could have used an efficient word rather than just saying sending secret messages. But make sure that I cannot use the word secure, cannot use. Why? Because secure communication means that if I have encrypted one audio using chaos and someone steals my audio, then yes, they cannot decrypt it or they cannot do those things. Okay. So that we cannot guarantee in this case. So therefore, it is not ideal to use the word secure communication. Okay, rather than like yes, sending secret messages is okay. All right. Okay. So this idea of how chaos can be actually used. Previously, researchers were using random noise. Random noise. Send they add some random noise, and that becomes totally random, and they are sending it, and people are decrypting it, and okay. But later, like Pecora and Carroll, like there are two scientists, Pecora and Carroll, in 1990s, I think yes, in 1990s they were from US and they both were working in naval laboratory, naval lab, but both of them were doing chaos, like nonlinear dynamics and chaos. They were researching on those. But naval companies, like naval people, the higher authority people, they asked Pecora and Carroll that, what are you researching on? So they told we are researching on nonlinear dynamics, dynamical systems, and chaos. They said, like they explained all the concepts, and they were like, oh, this is useful in naval. How this is useful in navy. Okay, so due to that, both of them started studying how you can how chaos can be used, how chaos can be used in case of naval, like some naval applications. Okay? So you can understand, like naval people, like when they are on the sea, they communicate information through some mics and all those things to the nearby ship. Okay, and when they are communicating voice, okay, it is transmitting through audio. Now imagine, I had this experience during my childhood. I will share it. But in the third party can intercept that. Third party can hear it. Maybe Pirates of Caribbean. Okay, Pirates of Caribbean, the Caribbean Sea pirates are coming and they are the third party. They were able to hear the sensitive information of the naval army and they will attack both of the naval army and take the ship. Okay, so this information has to be encrypted. Hmm? So, have you seen the interception of signals in any of your real life scenario? Anyone? No. Anyone who uh, had some sense that yeah, I am intercepting someone's signal? No. Okay, I intercepted it. I intercepted it during my childhood. Okay, I will tell you. I'll tell you this. So I'll draw some figures here. Okay. So this is my house. This was my house, like in Odisha. So this is my house. Okay, the building, and there was a nearby house which is of a bit of short height. Okay. Then there is another house which is like almost similar. Okay. H1, H2. Okay. This is my house. Okay. Now what happened is as I was a kid, my parents did not give me. We had a TV. Okay. My parents did not give me the Star channel. Star connection. Star connection, like you get additional channel apart from DD National. Okay, you get DD National for free. Okay, but plus I was getting zero. Okay, I was not getting anything. I was only able to see DD National. But the nearby house, they had ordered all the star channels, all star channels, all star, okay, all star channels. And what was happening is, funny thing is, isn't it? There is a one pole here, okay, in the ground there is a pole and there are a lot of wires, power line transmitting, right? So this house was given this power line, this house was given, my house was given blue power line, and maybe this house was given the green power line. Okay, understood this? So this was the power line, right? But I went to my terrace, okay, and I saw that there was a, okay, but I did not do anything. I did not have any knowledge of electrical or electronics engineering, okay, but unknowingly, these three wires are appearing to you very far apart, but they were very close to each other. Okay, they were very, very close to each other. Okay, these three wires. So you can imagine all the three wires are very close to each other. Due to that fact, by mistake, I went two ahead in hoping that I want to see some new channels. Okay, when I was watching movie. Okay, when I was watching TV, sorry. So I was in DD National, then channel button, then it went to a next channel, and it was just like that, random pixels. Some when the TV is going bad or something, you see that screen, no? Huh? What do you call that? Rays, gray, grains. So yeah, that. So those things you see. So I was seeing that, but I was positive that maybe I can see some channels. So I was putting it, but suddenly Cartoon Network appeared. Suddenly Cartoon Network appeared, but not in a good resolution, but in a resolution that I can see it. But I was amazed. Like my parents did not bring anything. Like how can I see Cartoon Network channel? Suddenly I was able to see Star Utsav, Sub TV, Sony, all these channels. Like a lot of channels I was able to see, and I hit a jackpot that day because yes, apart from national, I was able to see a lot of channels. Yes. So why that happened? My first question. Why that happened? Because these three lines, these three power lines are so close to each other that information somehow transmitted through these other power cables. I don't know how it is happening. Maybe due to the because these operate on the what you call that signal, no? What a DTH thing you have. If the two wires are close to each other, maybe the information transmits to the other wire also. Surprising, was very surprising to me. Okay, so this is one example where other person can interfere in what you are doing. Okay, other houses, H1 and H2, till now, maybe after some 20, 30 years, they have not yet known that I was watching the TV. Okay, so you can understand how information secureness is so important. Okay, so maybe when you will be talking in your house, other houses will be. So this is important, isn't it? So this is how, this is a small example of why securing information, and we will see how chaos could have been helpful in it. Anyway, so what they did is, let us return to this example. They showed that how chaos can be used in the naval applications. Okay. Then they thought that if you want to communicate information, one should be the sender and one should be the receiver, isn't it? Yes. One should be the sender and one should be the receiver. Yes. So if these two guys synchronize themselves, if these two get synchronized with each other, then yes, you have the information securely transferred to them, isn't it? If both are in unsynchronous manner, what does it mean? You are saying 5 now, and the 5 is coming to them 1 hour later. Understand that, right? It's just like the space thing. One star has one star is born One star is born now. We are seeing it now, like through telescope. But that doesn't mean the star is born now there. The light has traveled, light has took so many time to travel to Earth. Okay, maybe 2-3 years, star has already born. But the light is coming now due to the so far light years or something. Okay. But anyway, so synchronization of chaotic systems. That's what is needed. That's what is needed. Okay. Anyway, so what Lewis and Pecora and Carroll, they both did is they used the Lorentz system. Someone told about Lorentz system, right? Who? Which group told about Lorentz systems? Lorentz system. Someone told about Lorentz system, right? Anyway, so they used Lorentz system. Lorentz system to show the chaotic. They need a chaotic signal. And it was 1990s. It was 1990s, and remember, during 1990s, I think you must have known already that Lorentz was the famous scientist to show chaos. Okay, so therefore, a very easier thing to do is to take chaos from the Lorentz system. Okay, so Lorentz system, can you tell me, like, I'll just write these equations. That's fine. So okay. So this is something known as a drive system. Okay, drive system. And there will be a similar response system. So this is the same. This is the same sender and receiver. So this is the drive system. This is the response system. Okay. So it's the same. But here, what I do, this response, I am writing it as x sub r. Okay. X sub r, y sub r, z sub r. That means these are the variables of the response system. Okay. XR, I'm just writing it to be just x. It's the x from this guy. Okay, this is the x from this guy is fed into the x of the response system. Okay, that's how it is changing, nothing else. So you can see that both of them are holding hands. Can you understand? Both of them are connected. They are not disconnected because they are connected because I am using the x of this guy. I am using x of this guy here. Okay. Similarly, you can say like yr dot is equals to minus yr minus xt wherever x. Okay, it won't be xr because xr equals to x. Got the idea what I'm doing here? I will tell. So this is the drive system. From this x, from this data, I get x. This x I am feeding it to this response system. Okay, that means both of the systems are interconnected to each other. Okay, now xr is equal to x. So wherever you see xr, there you replace x. Okay, understood? So same zr dot, you can see it is x r y minus b z r. But since xr is equal to x, so I can rub it and write x. Okay, fine. Got this idea. Okay. Now assume that both of all the parameters are the same. That is r, sigma, b. All these are same in both the cases. Same in this case. Same in this case also. Okay. Now the idea is if both the drive and the response systems are synchronized. What does it mean? If both drive and response systems are synchronized, it means that XR, don't worry about XR because XR we don't have control. We have already set it as X. But what we don't have control is YR and ZR. So drive and response systems synchronize. If drive and response systems synchronize, if YR of T is converging to Y of T and ZR of T is converging to Z of T as time goes to infinity. Can you see? What does that mean? It means that both the systems are having the same value at a later time, isn't it? How many of you are not understanding this? Are you understanding or no? No? No. Imagine, see, there is always a thing to visualize this. Okay. Imagine Anandik is running and Halima is running. Okay, both are running in a race. Okay. So what will happen? What will happen? One of them will go ahead of the other. Both of them, if both of them want to synchronize, they have to have one foot at the same level. To synchronize themselves, what does it mean? It means that the one of the foot of both of them should be at the same level. That's the only way you can say that both of them are together in the same level. Yes, if Anandik moves ahead or Halima moves ahead and Anandik is lot way back, then they are not synchronized. Yes. So this is what I am telling you here. If both the drive and the response systems are synchronized, then it means that response system is slowly converging to the drive system. Yes, the response system is slowly converging to the drive system as time increases. Isn't it? Do you agree or not agree? So this is what I meant by synchronization of chaotic systems. Okay. But how we can do this? How we can do this? To do this, why YR and Y, ZR and Z, isn't it? If they go to zero, that means drive and response systems are synchronized, isn't it? Agree? Agree or no? Not agree. Agree. Okay. Okay. Can we show that they can agree? Can we show? Now I am planning you to show that indeed you will see that mathematically you can see that it will go to zero for these two Lorentz systems. That's the catch of this. Okay, that's the catch of this. How we can do this? So let us call this by some names. Maybe this is EY, this is EZ. Okay, maybe EX is X minus XR. So there are three variables I have defined now: EX, EY, EZ. Okay, those are the error terms. I want to monitor these error terms as time progresses, as time t tends to infinity. Okay. So if EY is equals to YR minus Y, what does the derivative EY dot mean? EY dot. It should be YR dot minus Y dot. Isn't it? Agree? Agree? Okay. Now what is YR dot from this? YR dot from this is equal to? Okay. I will write this expression. Let me know if this is correct. YR dot from this expression. You can expression. Okay. After you do this, let me know if you get this answer. Happening. No, the eraser is not working. So let me know if you are getting this value. Are you getting this value? Compute and let me know. Are you getting this value? If you are okay. Are you getting this? Anyone? Did you get this one? How many of you got? Just a simple exercise, minus things, nothing else. I want to show that EY dot is decreasing. One simple way to show that if EY is going to zero, I can indirectly show that the derivative of EY is less than zero. Okay. And then it will mean that EY is decreasing with time, and therefore EY is going to zero. This is the idea. This is the basic idea. Okay. So now, therefore, I am estimating EY here, EY dot, computing EY dot. I want to see how the error in the y variable is progressing. Did you get this answer? You got this. Okay. Now, can you tell me something more? How what I can do to y minus yr? It is EY, isn't it? X of t. What is z minus zr? Is EZ. Okay. Can you do similarly for EZ? What is EZ dot? EZ dot is ZR dot minus Z dot. ER dot is ZR dot minus Z dot, right? What is ZR dot? X Y minus BZ, right? Sorry, this is YR. XYR minus BZR. Yes. Minus Z dot is XY minus BZ. Yes. Can you tell me what value we will be getting? X into YR minus Y minus B, sorry, minus B into ZR minus Z. So this is equals to X into minus YR dot, right? EY, sorry, EY minus EY dot minus Z minus ZR. So it is plus B EZ dot, isn't it? Agreed? Agreed? Hope you agree. Did you agree? Yes. Okay. So can you check this again? All of you have done? Is any error is there in my case? Correct? Or some minus error is there? Is it correct? Sorry. Yeah. So you should get some plus, I think. I'm getting some plus or something. But are you getting exactly this? I don't think so. You are getting exactly minus minus xt ez. Oh, oh, is it? No. Ey is yr minus y I have defined. But here it is y minus yr. So it should be plus. Z minus zr minus ez. So it should be plus. See this definition over here. Okay. Agreed? Agreed, right? Let us now see what is this value. Now we got EY dot and we got EZ dot. Okay, both of them we got. Okay, now let us try to see what is EY dot times EY plus EZ dot times EZ. Okay, what is this value? then you will come to know that yes, indeed, there is a technique I want you to know. Okay, just have patience a bit. So Ey dot times Ey plus Ez dot times Ez. What is the value? Can you tell? If you do quickly, we can finish quickly. What is Ey dot? Ey dot is Ey plus x Ez. Okay. Then Ey is yr minus y, right? Plus. It is better to keep Ey itself. Plus Ez dot. Ez dot is, can we solve this? Ey square plus x Ez Ey. Uh, so there is no dot here. Minus x py Ez plus b Ez square. Okay. Note that these cancel out. So this is Ey square plus b Ez square. Okay. Fine. Okay. Now this is an exercise to you. This is an exercise to you. Can you write this as half into Ey square plus Ez square d by dt? Okay. This is just d by dt of half Ey square plus Ez square. And this derivative is coming out to be this quantity. Okay. So what you can understand from this? That's my question. So after this, I won't do the step, but mind you that this derivative will be decreasing. Okay. Therefore, the derivative is decreasing. Derivative decreasing. Therefore, you can say that Ey goes to 0 and Ez goes to 0. Okay. If Ey and Ez goes to 0, that means the drive and the response systems. This is very surprising result. This is a very surprising result. Why it is a surprising result? It is a surprising result because in Lorentz system, whatever parameter you take, whether it be sigma, R, B, whatever parameter you take, only because you are holding the two systems, you are connecting the two systems, drive and response, by the X signal. You are connecting it by the X signal, right? Only by the X signal, and therefore this is the main reason why both of them are synchronized. Whatever parameters you take in your drive and response system, because XR is equals to X, therefore this is the main reason why both drive and response system are synchronized. So this is something like very fascinating result and led to the theory of network of oscillators, which many project students are doing right. Okay. So if you see, like now, since two groups are interconnected, drive and response, okay, and we found both of them are at sync. This terms of ring of oscillators. Okay, what happens if you have a ring of oscillators? What happens if you have, say, a chain of oscillators? What happens if you have a random network of oscillators? Random network means in the sense that, yes, like a power grid. Power grid is the best example where you can apply your network theory concepts. Those who are doing the mini project with spiral and target waves. If you see the power grid of this, of maybe Tiruvandapur, okay, you will see it is a very nice, heavy, random kind of a network. Random kind of network. And it is to study the network theory of oscillators, okay, because each power grid will be transmitting power grid, okay, and if one power grid fails to transmit the current, then there will be a blackout. there will be a blackout phase. In a very tiny phase, yes, normally you must have seen in the house that your 10, 15 households, the power is gone. Terrace and see only after some houses, they are enjoying the TV. Okay. Then you say that, what, my house doesn't have power, how come their house has power? Okay. So if your household has the power gone, that means it will affect a neighborhood of that. It will affect a neighborhood, whereas these power people will have the power. Okay. So this is how the network theory evolved. Okay. From considering the drive and response system in communication to the network system of power grid. Okay. So yeah, you can always generalize this information to have more and more networks. Okay. But finally, to understand all this, you need this graph theory concepts. Okay. Like adjacency matrix, like all those degree of a node, degree of a graph. Okay. What are the ingoing and outgoing nodes? Okay. What is the degree of a node? Okay. How one node is more, what is the degree? If more nodes, more information is coming to one, it has more degree. That means it is more loaded with information than other nodes. Okay. So you can see that suddenly knowing one small idea can actually generalize into bigger ideas. Okay. That's what it is on synchronous. Also, like how you can use it to communicate secret messages. Okay. I'm not going to detail, but to these systems, you can just some M of T. This is known as a mask. And comes from a chaotic system. Okay. So this mask, I told you about the environmental noise. Okay. If library, in your library, mask is very close to zero. Library. Okay. But in markets or any public place, M of T is very high. M of T is very high. Therefore, masking is very high. Therefore, you can transmit the secret information quite easily in noisy environment or in masking environments. Okay. So this is something known as masking in audio signals. Okay. Quickly, I think our student group can show the application of video encryption. Yes. Or